Hi everyone. So today's topic is going to be comparing distributions and normal models. So in the last lecture, you learned about histogram and box plots. So after you visualize the data using these tools, you might want to compare different distributions or groups or conditions. And how would you do that? And what are the considerations for doing that? So in this topic, in later lectures, you are going to learn formal statistical tests to compare groups and conditions. But in this lecture, you are going to learn about what are the things that you need to consider and you need to know for the comparisons of different groups or conditions. So I want to start with this data. So in this data, the x-axis is average wind speed and y-axis is number of days, and this is histogram and this is 5-number summary. For this data, we need to know the context. So it is the data are collected during 2011. These data were the average daily wind speed. The unit is mph, mile per hour, where it's from Hopkins Forest in western Massachusetts. And why? They wanted to do the long-term observations to study ecology and climate. To know more details about this data, we can divide the data into seasons, because we know that the wind speed is depending on, can be different across seasons. So this is spring, summer, and this is fall, winter. As you can see, the fall winter has more higher values. And to more effectively compare these patterns, we can actually put this data into this format. So x-axis here is month. So January, February, March. So x-axis is about different days, different time points within a year. And y-axis here is average wind speed. So the plot has been changed a little bit, and we want to compare each the time points, right? And one thing you can observe here is so these, as you learned about the box plot, these dots are outliers, but this outlier here is defined within the context of April, and this data might not be defined as outlier in January, right? So the important observation here is outliers are totally context dependent. So outliers should be defined depending on different context, considering the context. So that's one thing we need to know about outliers. So to compare different groups and distributions, we really know what outliers are. So outliers is the definition of outliers is the values that are located far from the main distribution. And outliers may be the most important values, maybe, but also it could be just errors. But the challenge here is it's really difficult to know which one. So what to do with them? So we need to go back and go back to the raw data or the measurements or the equipment and so on to make sure the outliers are not the errors. And if it turns out to be errors, for example calculation errors or other measurement errors, you can correct them if possible. But there are many occasions that you cannot really correct them. So in that case, you need to report summaries and analysis. So some statistical analysis with and without the outliers. And when you report your research analysis results, you can report them with and without outliers and say, oh, these results are with outliers and these results are after removing the outliers. and so that readers really know what's going on and readers can decide later. So it really gives the responsibility to readers. You can decide whether it's error or important values. Or there are some statistical methods. Some are really useful. We don't use them every time, but we sometimes use them. Some methods can downweight the outliers. So for example, there are many robust methods. For example, robust regression. It is doing regression. Regression, we are going to learn that later lectures. But when doing regression analysis, we can downweight the outliers. That is called robust regression. Or we can also do the smoothing. I'm going to tell you about smoothing in a minute. But by smoothing, we can actually reduce or remove the outliers. Smoothing is really powerful method, and so we use it a lot. So smoothing is basically make the data smoother. Okay, using some kernels and window moving averages. I'm gonna tell you about moving averages in this lecture soon. The things you shouldn't do, never do. So one thing is leave them in the place and proceed as if nothing were unusual. Just do nothing and then tell nothing. Don't do that. And omit the outlier from the analysis without comment. This is another bad thing to do. That's modification of your data without any comment. And there are other methods that can help the comparisons of different distributions. One of them is re-expressing data. That can be used to improve symmetry of the distribution. So to compare many different distributions, making the distribution symmetrical really helps. So let's take this data as an example. So here the x-axis is annual compensation, so annual income, basically salary, and y-axis here is number of CEOs, and you can see the data is really right skewed. It has a long tail on the right, and there's an outlier here, a really rich CEO. And if you take the logarithms of these values, you can make this distribution more symmetrical, right? So in this way, you can use many different statistical analysis methods that are developed for this symmetrical distribution easily, right? Effectively. And this type of normalization, it is called normalization. Normalize the range and spread and values. And it's very common in physio data pre-processing. In our lab, we are collecting a lot of physio data, psychophysiology data, called, for example, SCR, skin conductance rate. That is the sweat on your finger or hand. When you feel something very positive or negative, you are sweating. So we can measure that. Or heart rate using ECG. And you have some emotional experience, your heart is going to be racing. And you can think about this as a really right skewed distribution, because really low heart rate is impossible. Yeah, you are going to die. But your heart sometimes really fast, right? Become fast. So it's really right skewed distribution, and therefore to help analysis, we are commonly take logarithm or square root to normalize these values. And also you can use re-expression of data to equalize spread across groups. The spread here means is kind of like standard deviation, something like that. Standard deviation, how spread it is, the data is. And I want to use this data. So here the x-axis is smoke exposure. So it's a secondary exposure to smoke, and the y-axis is catenin. It's I think it's related to nicotine, but like the previous format of nicotine. And you might not be able to compare these distributions because it's too squashed. So it's, I mean, there are too many values here, not many values up here. But the distribution is so different. If you take the logarithms of these values, as you can see, the spread became similar, right? And so you can easily compare these different distributions. Interestingly, the normalization has been one of the key elements of recent successes of artificial intelligence. And we started with the time plot actually, and I want to explain more about time plot. And we really want to compare these different distributions for different time points. So what is the time plot? The time plots has the values against time. It's time series data. There are so many different time series data, and it's really common. For example, neural activity data, that is time series data because we are recording neural activity across time, over time. And stock market data is basically the values of stocks over time, right? And biosensors. And how can we effectively compare these data? So this is raw data. I mean, box plot looks much better and makes the comparisons easier. But this raw data, this is processed data, right? The box plot, and this is raw data. And you might want to just connect the dots, and then it's because it seems really noisy and hard to interpret. And what we can do is really the smoothing. We can do smoothing using the moving average, so moving window. We call it as moving window method. So we make a window and then get the average value, and then move again a little bit and then get the average value, and move a little bit and get the average value, and so on. And like I want to show you this. Move along the x-axis. Oh, it's not working. Okay, so anyway, the window moves along the x-axis and then plot the mean values across time, and then you can get this smooth line. This is basically the moving window average method, and another method is locally weighted scatter plot smoothing. So you call it LOS or LOS. So these methods are being used in the field very commonly in time series data, for time series data. Okay, so by doing this, you can easily see the patterns. Like during the summer, the wind speed goes down, and then during winter it goes up. So you can find the pattern easily. Okay, so that was chapter 5. We learned about outlier, and that is context dependent, and how to re-express data that will help the comparisons of different distributions, and also time plots and moving window. But what if we want to compare two distributions that has totally different units? So we can use Zscores for that, to compare different values in different units. So we call Zscore as a standardized values. So here, standardized value. So standardized in Korean is 표준화. So we are standardize these values by subtracting mean from the data and divided this value by standard deviation. Here S is standard deviation. By doing that, we are getting Z-scores with mean 0 and standard deviation equals 1. This means that we are using standard deviation as a ruler. So ruler means just one unit. That is actually standard deviation, like SD or S standard deviation. So one standard deviation is basically 1. in this standardized world. So in Zscoring, there are two elements. One is shifting and the other is scaling. I'm going to explain what they are using this data. So this data are the weights and number of men, weights collected from 80 male that has similar heights and similar age, and the unit is kilograms, from United States, and to study nutrition and health issues and trends. Okay, a researcher wanted to subtract the recommended weights from these values. By doing that, you are getting different plot. The meaning of x-axis change it, right? So that now it's kilogram above recommended weight. So you can easily see that this person, for example, this person got the kilogram far above recommended weight. But the distribution is same, just it's a shifting the values, just subtracting some constant from the value, from the data. By doing that, the distribution is just shifting. But you might want to change the unit, because in the United States, people are using pounds usually, and therefore you might want to change kilogram to pounds. And the distribution is changed a little bit, but just scales are changed. The distribution is same, but scaling is changed. So this is rescaling. Basically, these two components are involved in the Z-scoring. How can we know how big the Z-score that I got? This is an example. Let's say you've got a Z-score of 3, and how surprising your observation is. We really want to say this because we want to know, we want to compare the value based on something and then say, oh, my data is so surprising, or my data, the results I got is not that interesting, right? To answer this question, you need a model of your data distribution. So we are going to use a normal model, but before that, we need to know this. This is a really famous quote from George Box. All models are wrong, but some are useful. So the models is based on theory or parameters, population parameters, theoretical parameters, and then the model are just drawing a really beautiful world. In the ideal world, for example, the heights or the weights really has these bell shapes. But in the reality, there are noises and there are many complicated factors that are influencing this data, and it has a complicated interactions. So the data cannot really have this shape, but this model really provides some anchors for us to judge my data. So the most popular model around the world, around the field or around research areas, is a normal model. This bell-shaped curve. You might learn this from your high school. So that is a unimodal and symmetric. It's a symmetry. We usually use this notation to say to describe the normal model. So here, mu is mean and sigma is standard deviation. So n mu sigma means this distribution that has a mu as a mean and standard deviation is sigma. Why Greek? Why we are using Greek here all of a sudden? And these are parameters of the model. So this is theoretical values about the population, not numerical summary of your data. So we are assuming that the data is from that population level theoretical, the population data. So numerical summary of the data, we are using these notations, y bar and s, or STD, or standard for standard deviation, SD, whatever. But here we are using S. But for Z-score, we can calculate the Z-score in theoretical way. But theoretical Z or numerical summary Z, all are Z-score. Okay, so we are saying Z is has theoretically normal model with mean 0 and standard deviation 1. And actually, using your data, you also make the mean 0 and standard deviation 1. So it's the same, basically. So this is standard normal model. Okay, so this left side is a numerical summary and right side is a model. So to use normal distribution, normal model, we need to check the normality assumption. All models make assumptions. These assumptions should be carefully examined whether my data really meet these assumptions or violate these assumptions. We need to know that. But for the beauty of normal model, we don't need to meet all the assumptions exactly, but it's enough. That's a nearly normal condition is enough. It's sufficient. So just good enough to be used as described using the normal model. And what is nearly normal condition? The shape should be in unimodel and also symmetric. This is basically that, and then this is the way to check the shape. It's a shape. We can use the histogram. We learned about histogram and normal probability plot. We are going to learn this soon. To learn that normal probability plot, we need to know this first. How to change Z to probability or probability to Z. So we need to learn this. So this is a theoretical normal distribution. It can be expressed like this equation, and here for Z-score, mu is 0 and sigma is 1, but here just let's say mu is 1 and sigma is sigma. Okay, and there is a 68, 95 and 90.7 rule. That is Z equal 1. That is the area within the one Z-score equal 1 is 68% of data fall within this one standard deviation, and 95% data fall into within the 2 standard deviation. So that is Z equal 2, and Z equal 3, 99.7% fall within this 3 standard deviation. So this is the probability or proportion, and so Z-score equals 1 means if you got the Z-score 1, you are 84%. Why? Because it's including all the area below Z equal 1. So you need to subtract this area, so that is this 68 divided by 2 from this 50, the half of the distribution, and then you get this, right? You get this area, and then you subtract this from 100, and then you get this. So that is 84%. And yes, that's the meaning of Z equal 1. So you can see this easily from website. Actually, I wanted to show you the website. You can just Google the Z, let's say Z2P, and you can go to the first link, and here you can just put 1 for Z value and calculate. And between the area between +1, so plus minus Z is the 68, so 68%, right? Or the below the area, that is this, and so you can subtract this value from 100, and then you can get 84, and or you can calculate z equal 2 or z equal 3. Okay, so let's see 2 95% and 3 99.7. so it's basically this 68 95 99.7 rule. So remember these numbers. Why we are doing this, we need to know the z to p value. You will see how I use this. We are using this for normal probability plot. So before we draw the normal probability plot, we need to find normal percentiles. We can use the table of normal percentiles. That's table Z in appendix D of the textbook. So in the table, let's say you got the 1.8, Z equal 1.8. You can get to the 1.8, and then the decimal point is 0, right? So because of that, you can get here. So 1.80 is 0.9641. Or Google it. You can Google Z to P that I just showed you, and P to Z is same. So table Z again. So use this. So you can also here you can type P to Z, and then you can see you can convert Z to P or P to Z. But you need to know this concept. Z equal 1.8, and P means that means among the 100, what is the percentage of the area below Z equal 1.8. Okay, so we are ready to draw normal probability plots. So what is normal probability plot? It's original value against normal scores. What is normal score? That is theoretically expected value. So theoretical normal score, theoretical z-score, basically. It's similar to QQ plot. There are many different ways of calling this plot, like PEP plot. This is percentile plot, or QQ plot, that is quantile plot. Okay, so here, let's say you got the mile per gallon. So it's a YUMB for cars, and this is a distribution of the MPG. And you can calculate the percentile using this. So sort these values, this data, sorting this data, and then you can calculate the ranking, right? Ranking the first one or second, third, and so on, and then you can get the percentile from that, right? How, like, percentage of the location of the data, each data point, and then based on this you can do P to Z. Is P to Z is according to the normal model, what is the Z value for this percentile, and then that Z value goes to here. So you have each data point, and you have each Z values for each data point. Theoretical Z values, theoretical. It's based on theoretical, based on the normal model, right? And just plot those, and then if the dots are on the straight line like this, this line, it means it's symmetric. And this is skewed data, and it's not on the straight line, it's bent. That means it's skewed. If the dots are not on the straight line, that means it's skewed. So these normal probability plots are really good at examining whether the data are symmetric or not. Okay, so we learned about the many considerations like outliers, how to re-express data, time plots, and smoothing, and also normal model Zscore that has two components: shifting and rescaling, and we learned about normal model is theoretical model, and that has an assumption, unimodal, and symmetric. And we learned this Z to P, P to Z, and in the class we are gonna actually spend some time to learn how to draw normal probability plots. We are gonna actually draw these normal probability plots in the class. Okay, I'm looking forward to it, and see you in the class. Bye.